Hey everybody. So second week, here we go. Got some people in office hours and we got a couple questions to go over so far. We got mastery question set 2, looking at problems 2, 3, and 5, and I'm going to do those in a different order. We're going to start with problem 3 and 5. Those are both kind of review problems from last week. I almost said last quarter. Jeez. From last week. And then we'll take a look at problem number 2, which has a lot of information needed to actually do that problem. So let's go ahead and get started. Now, mastery question 3 is a Beer's Law problem. Actually, 3 and 5 are both Beer's Law problems. And, Mario, I think you're going to kick yourself when you see the trick to this one. But we'll see how it goes. So this problem has a graph given to us, right? Just like the Beer's Law plots that we made for our prep activity, we've got concentration, and we've got absorbance. We've got some data points. I don't know if everyone's data is the same or not, but we've got some data that looks like that. And then we've got our best line fit that kind of goes through as much of the data as possible. And we've got an equation for that of y equals 0.12377x plus 0.0107. Those are the numbers I have. I don't know if you have the same numbers. But the trick to this, and the problem is asking us to calculate the molar absorptivity. And from what we remember from Beer's Law last week, hopefully, is for the equation of a line, y equals mx plus b, that is our mathematical understanding of Beer's Law. And we can overlay with that our conceptual understanding of what Beer's Law is. Sure, that's okay. Beer's Law is on the equations sheet. We used it a lot last week. And that is A equals epsilon, weird looking epsilon. A equals epsilon b c plus 0, right? There's no plus there at the end. And I tried to write this in a particularly suggestive way, where my y-axis lines up with what's on my y-axis. My x more or less lines up with my x. And then my slope should be epsilon times b. Now, here's the kicker. It's asking us to calculate epsilon in units of, sorry about that, I'm getting some alerts as well. I started a conversation on something. It's asking us to essentially get epsilon in units of 1 over molarity times centimeter. The concentration, though, is given in nanomolarity. So really, the slope should be epsilon, but we're off by our units. And that's kind of it. So all we actually have to do to solve this problem is recognize that we've got 1.9767 times 10 to the minus 4, and that's going to be rise over run, so no units, over nanomolarity centimeters. And you'll notice the units don't match by a factor of 1,000,000. And that's kind of the only thing we have to realize. And then we say 1 times 10 to the 9 nanomolarity per molarity, right? Because the nano is that prefix. Yeah. You could have done a -9 on bottom, but 1 times 10 to the 9 nanomolarity per molarity. You do that multiplication through. I should be able to do that in my head because it's just going to be 9 minus 4. So you should get 1.9767 times 10 to the 5, 1 over molarity centimeter. Now, if your number's different, you of course have to do it for your numbers. I don't know if this problem has randomized values. But the kind of trick here is recognizing, so it's a reminder of how we recognize our mathematical understanding versus our kind of physical, chemical world understanding, and then just watching out for units. One of the things to keep in mind, the values we typically expect for epsilons are between, if it's in units of molarity, are typically between 10,000 and 100,000. So when we see this number, we should know that something's wrong with the units. And when we look at this, this is going to be if 1, 2. So this is going to be at like almost 200,000. So this is a pretty big epsilon, unless I'm off by a 0. Nope, that looks right. So it's a pretty big epsilon, but it's still in that ballpark of more what we expect. So that's problem 5. Did your values work? Cool, great. I saw the nod. Problem 5 might have the same issue, right? So problem 5 flips our understanding a little bit. Does an absorption plot rather than a Beer's law plot. What's the difference? Well, an absorption plot is where we are varying the wavelength and looking at the absorption, and we get some peak. I'm not great at drawing these things. It's at a lambda max is equal to, it gives us a value for lambda max, I believe. No, it does not. It just asks us to find the value at lambda max. Lambda max, I'm going to guess, is at about 510 nanometers. But that part doesn't actually matter that much. After we know where it is, if we went to a different wavelength, we'd get a different epsilon because the absorbance would be different. But as long as we're always at this wavelength, we should always get the same epsilon. And again, this problem is asking us to calculate epsilon. So this is mastery question 2, problem 5. Beer's law question. We're still going to have this idea of A equals epsilon BC. It tells us the path length is 1. It tells us the concentration is 573. It's asking us to find epsilon, so I'm going to just leave that as an epsilon. And it doesn't tell us what the absorption is. We have to estimate the absorption off of the graph. And again, I don't know if this is randomized for the different graphs, but on my graph, it's about 2, maybe 2.1. So I'm going to say my absorbance is approximately 2.1. And right away, and this is one of the important things we have to be careful about. This is going to be a theme throughout these office hours and throughout this week. We have to be careful about just crunching numbers versus what it physically is trying to represent. We're going to see that a lot in your question, Jennifer, the mastery question set 2, problem 2. There's a big difference between being able to crunch the numbers and understanding what you're trying to represent. And here, again, it becomes a trick of units. I intentionally left my units off to kind of be tricky. This is in centimeters. This is in micromolarity. So again, they switched the units of concentration on you. And then this has no units. So if we just divided over, we'd be off by a factor of 1,000,000. Let's go ahead and see what would happen if we were off by a factor of 1,000,000 real quick. We've got our epsilon is going to be equal to 2.1 divided by 1 times 573.
I'm not sure if this matters, but is the path length 1 centimeter or is it 1 millimeter?
Oh, that totally does. Oh, what a tricky problem. I was looking at it so quick, I didn't even notice that. So I would have made a different mistake. They changed 2 things on us. Yeah. Thank you for that. I'm going to put that in orange because I made that mistake. That's in millimeters. So we're going to have 2 mistakes here when I do this division. So let's do 2.1 divided by 573. And we're going to get a value that's like 3.66 times 10 to the minus 3. Right, and right away from our expectations of epsilon, we should know it's not between 10,000 and 100,000. It's not even close to that. So something's off with the units. And there's actually 2 unit mistakes. The millimeter, which I almost missed, thank you for that, Jennifer, and the micromolarity. So let's go ahead and do it the correct way. But you notice the thing I wanted to stress in doing this was we can, by reading the textbook, by going through sample problems and kind of being thoughtful as we do them, we can come up with reasonable expectations of what values should be. That way, when we get something unreasonable, we know we made a mistake and we can do it again. So let's go ahead and actually do it the right way. Where the right way is actually going to look very similar. Epsilon is equal to 2.1 divided by 1 millimeter. I'm just going to put my unit conversions right in there. 1 centimeter has 10 millimeters. Oh, that's an M, I swear. And then our 573 micromolarity, we want to convert that to molarity, is going to be 1 times 10 to the minus 6 molarity per 1 micromolarity. So you'll notice you'll actually get 3.66 again, because all that's changing is a factor of a 10 and a factor of a million. So that's going to be -7 divided by 1 times -7. And then, if I did my calculations correct, there's 3 people here, I encourage all 3 of you to do these calculations as well. 3.66 times 10 to the positive 4. I got my units scrunched in there, but notice the only thing that changed is that order of magnitude, and now we're at 36,000 instead of 0.0036. This can be a really frustrating, being careful with your units is super important. This can be a really frustrating thing. It's actually really difficult for instructors to figure out what's going wrong when this happens, because it looks like you've done everything right, and then it just creates a mistake. One other thing I'll mention to be really careful about is to make sure that you're being careful with your parentheses when you're doing your multiplications in your calculator. A lot of times, if you have the times 10 to the, if you have 1 times 10 to the minus 6 outside of like a parenthesis on bottom, it'll take this whole value and it'll multiply that on top rather than dividing it. So you have to be careful with your calculators as well. Did it work out for you?
Yeah. Thank
Great.
you.
Okay. Now, okay. Mastery question set 2, problem 2. This is a big one. This gets to kind of the core fundamental idea of what we're doing this week. So if you haven't watched Dr. Neff's video on line spectra, and if you haven't watched Dr. Scott, I think it's Dr. Scott's video on the Bohr model, this problem just assumes a whole lot of knowledge right off the bat. So we're looking at mastery question set 2, problem 2. And in terms of how long the problem is, it seems like it should be really simple, right? Calculate the wavelength of a photon that is produced when an electron drops from n equals 5 to n equals 4. That's it. But the amount of information, the amount of chemistry buried inside of that problem is huge. So let's go ahead and write down the things that we know for sure out of this problem. We want to calculate wavelength. We want to calculate wavelength, and we do it in a silly unit. I don't like micro. Oh, I know why we do it in that. So we're doing it in micrometers, making sure that I've got that nice script for the micro, and that nice lowercase m so we don't confuse it with the molarity, the thing we were doing in the last problem. And then we're also told n equals 5 to n equals 4. Now, what the heck is going on here? Now, there's a lot going on in order to solve this, right? This is getting at the fundamental connection between light and atomic behavior. So we have to understand something about light, and we have to understand something about the way the atom behaves. In terms of the light, behavior, we've got Planck's constant, Planck's equation that kind of describes how light can be thought of in terms of having discrete packets of energy. Revolutionary kind of thinking in the early 1900s changed everything about the way we think about the physical world. Maxwell Planck was actually not believed when he first came up with this idea. They thought that this idea that the energy of a photon is equal to hc over lambda, when he did this work, it was thought to be a coincidence. They thought like, oh, that was just a weird coincidence. There's no way that could be right. And it was 10, 15 years later that Albert Einstein came by and actually got the exact same result as him. And people started being like, oh, well, maybe this is real. So this is kind of, we're just going to take that equation for light. That's the energy of the photon. The big change here, most wave properties, if we're thinking about sound waves, ocean waves, anything like that, most wave properties carry extra energy in their amplitude, but light carries extra energy in its inverse wavelength or its frequency. So there's this fundamental change in the way that we think about light, and that has a bunch of consequences. The second thing we have to think about is the atom and the atom energy. This is going to be really important for looking at the Bohr model. So Dr. Scott does a really nice video on the Bohr model. I think there's one from Bozeman Science as well. I can't remember where the second video is. But what we have to kind of get at is that you're going to end up with this kind of weird equation for the energy of an atom. I'm going to look at it on the equation sheet because I don't have these things memorized. I probably should because it's actually not that hard of an equation. Negative RH times 1 over n squared. Seems simple enough. But this equation, and there's two ways we can think about this equation. The first way that we can think about this equation was it was just observed, right? So a lot of the work that we're doing and the way that we're going to look at this problem is actually in terms of the Rydberg equation, putting these two things together. And again, Dr. Zneff's video on line spectra goes over that. But essentially, when Rydberg first came up with his understanding of this, it was kind of just a way that worked. Saw a bunch of lines coming out of a hydrogen emission lamp and saw that they came out with this like 1 over n squared kind of value. Didn't know why it was happening like that, just saw that it was. We now, with the advent of quantum mechanics, we now know that by treating the electron, so we've got our nucleus, we've got an electron. By treating the electron, rather than treating it like a particle with one spot where it exists, by treating it like a wave that kind of has like all of this space where it could be, and it's kind of not really moving in one spot, but has this like wave behavior, we can use this idea from quantum mechanics to actually get this equation just from mathematics. Beyond the scope of this class, I've probably already talked about it too much, but I love this stuff. Fundamentally, what it comes down to is in order for the electron to be stable around the nucleus, it essentially needs to have exactly a sine wave. I think I didn't give myself enough of a wiggle. Hang on. Let me think here. So it could be like that, where you notice if I come back, if I brought this point at the end over here, it would just repeat again. And if I bring it back, it just repeats again. So that's going to create this stable kind of standing wave. Or, so we've got this like n equals 1 situation. Or, ooh, let's see if I can do this now. We could have this situation in blue, kind of sloppy, but this would be twice as many wiggles, right? So this would be like an n equals 2. And we need to have these kind of stable, we need to have these kind of repeating patterns that are like sine waves in order to have a stable electron around a nucleus. This idea is part of why we end up with this n value here. And why n is n is an integer, right? So we're not going to have like half waves or quarter waves or 2 1/4 waves. It's going to be 1 wave or 2 waves or 3 waves or up to n waves, right? Where it could be any number of waves till we get to like a crazy trillion waves, but it has to be a whole number. So that's kind of I usually spend 2 hours talking about or not 2 hours. I spend like probably 20, 30 minutes talking about this equation. But for us, all we really need to know is there's a constant that relates the energy of a stable orbit to the energy of the atom. Any questions about that? That's kind of is a really hard concept to wrap your head around. I encourage you to read it in the textbook, watch the videos, ask more questions about it. It's one of the strangest things in this class. Okay. So how are we going to put these two things together to actually solve the problem? Well, I like to make an energy picture. You notice there's a negative sign. That's because when the electron is attracted to the nucleus, there's an amount of energy we need to put in to get it away and an amount of energy we get out when it comes in. And I like to draw an energy picture. I'll try to scrunch it over here. So I've got my energy on my y-axis. And then I'm going to have that n equals 1 case. And with this equation, we could calculate the energy associated with n equals 1. Given the Rydberg constant. Another thing I'll warn you about, there are 2 versions of the Rydberg constant because there's 2 versions of the Rydberg equation. But the Rydberg constant, if we're using the energy version of it, is 2.18 times 10 to the minus 18 joules. Right, so we can plug in 2.18 times 10 to the minus 18 joules. We can plug in n equals 1, and we can calculate the energy at this level. I'll just write it in. 2.18 times 10 to the minus 18 joules. Then we could go to n equals 2. Our next stable kind of wave function, or wave pattern that's going to be stable. In that case, it's going to be 2.18 times 10 to the minus 18 divided by 2 squared, right? 1 squared was 1, that's why we got the same number. So I'm going to go ahead and plug that into my calculator. 2.18 times 10 to the minus 18 divided by 4. And I'm going to write this in a little bit of a funny way. 0.545 times 10 to the minus 18. I want to leave everything in the order of 10 to the minus 18 just so we can compare it. Joules. Good so far? Now we're just going to keep going up. We could just keep going. N equals 3. N equals 4. N equals 5. And what this problem, for the version of the question I have, I want to do n equals 5 to n equals 4. So I'm going to have my atom change in energy between those two. And I want to find the difference in energy between n equals 5 and n equals 4. So we can kind of set this up as a change in energy calculation. The change in the energy of the atom is going to be the energy of the final state minus the energy of the initial state. Or if we just plug in our n equals 5, n equals 4, that's going to be energy 4 minus energy 5. Notice that energy 5, notice that it gets smaller as we go up. Our energy gets closer and closer to 0. Oh, and also, I forgot my negative sign. Don't forget your negative sign. So energy is going to get smaller and smaller as we go up. This gets us to one of the versions of Rydberg's equation. One of the versions of Rydberg's equation essentially says the change in energy in that, going off of the equation sheet, says the change in the energy of the atom is equal to negative Rydberg constant times 1 over n final squared minus 1 over n initial squared. This version really has the kind of quantum mechanics built into it. And at this point, I can just plug in n final, n initial. I can plug in my 4 squared, and I can plug in my 5 squared there.
I have a quick question, sorry.
Sure.
Where did you get the negative RH equation from?
So I got that. There's two ways we can get it. Fundamentally, we get it from quantum mechanics, right? We get it from a long, drawn-out mathematical process, that kind of weird thinking I was doing on the side. For us in this class, we can grab it off of the equation sheet, and we can grab it for the individual atomic levels, or we can grab it for this Rydberg equation in terms of difference in energies. And after we do this calculation, we'll look at it another way too.
I think I'm just wondering, so the equation that I see on here that's most similar to the one that you're using is the delta E equals negative Z squared times RH times...
Yes. So
do we need the Z squared on there? Or?
So typically, okay, so I left the Z squared out, and actually I just noticed this problem does not say for hydrogen atom. But almost always when we do this calculation, it's for a hydrogen atom where Z equals 1.
Oh, okay, got it. So it's just, okay.
Yeah.
So we don't need it.
So there are some weird situations where you could do like a lithium ion or beryllium ion, and then Z would not be equal to 1. But for most cases, unless it explicitly says otherwise, Z is going to be equal to 1 for us.
Got it, okay.
So you can see the delta E, and I like to say it's the delta E, it's the change in energy of the atom specifically. And then we've got the Z squared is just equal to 1, then I've got my negative RH, 1 over n final squared minus 1 over n initial squared.
Got it, okay.
Cool. So what this is going to allow us to calculate is the change in energy of the atom. If we agree with what are considered some of the greatest minds of our of beyond our lifetime, of the last century, hydrogen atom is going to have this kind of discrete energy level idea, and we just have to find the difference from the 5th level to the 4th level. Pulling the constant out, we can do 1/4 squared minus 1/5 squared, which is going to give 1 divided by 16 minus 1 divided by 25. That's going to give us the delta E of the atom is equal to negative 2.18 times 10 to the minus 18 joules times 0.0225. Notice this is for the change in the atom. So now we've got this change in energy of the atom. We've got this part. We now have to relate it to the light up there. Good so far? And then we'll do this using the other equation as well in just a moment. So, let's see. I'm going to finish calculating that, actually do my multiplication times 2.18 times 10 to the minus 18. So I get 4.905 times 10 to the minus 20. I'm just going to plug that in here. I got it from that calculation, and there's a negative sign there. That negative sign, wait, is there? Let me make sure. Yes, there is. So what that negative sign tells us is the atom is losing energy, right? That's the change in energy. The atom is negative. The energy is dropping, right? So the atom is losing energy. When the atom loses energy, it loses that energy as a photon. So we can now bring in this other equation of how this relates. And this is kind of another big, like, whoa moment, is the way that the atom energy and the light energy relate to each other. And I actually, last quarter, I had a kind of like big whoa moment with this, because I realized when I was doing this calculation last quarter that all light that exists is because of this. All light that we see, all light that we observe, comes from electrons interacting with nuclei to produce light. The sun, campfires, your laptop screen, light bulbs, all of it comes from electrons interacting with the nucleus. All light comes from this. Whoa. So one of the things we have to realize, though, is light is not going to have a negative energy associated with it. Right? The atom is losing losing energy, and we're getting the energy of a photon. Equal to the energy of an atom. But the photon energy always has to be positive, so I'm going to take an absolute value. We have to be careful because, and you can think about it pretty clearly, right? Whether this was going up or down in terms of its energy, whether it was going 5 to 4 or 4 to 5, that change in energy should be the same. That means that photon energy for absorption or emission should be the same. Even though a different thing is happening to the atom. So whether the atom's gaining energy or losing energy, that photon energy should be the same. So that's where that absolute value comes from. That's going to allow us to say 4.9, notice that just gets rid of the negative sign, 4.905 times 10 to the minus 20 is equal to 6.626 times 10, oh, I didn't give myself enough space. Let me give myself a bit more space here. I forgot how long these constants are. So we're going to have 4.905 times 10 to the minus 20 joules, I'll put units on there too, is equal to 6.626 times 10 to the minus 34 joules seconds times 2.99 times 10 to the 8th meters per second divided by the thing we're trying to solve for, wavelength. Notice when we do our rearrangement, we'll get lambda equals 6.626 times 10 to the minus 34 joules seconds times 2.99 times 10 to the 8th meters per second divided by 4.905 times 10 to the minus 20 joules. Joules will cancel, seconds will cancel, we'll get something in meters. Right? And it makes sense that we'd get a wavelength in meters. So we plug in all of that, takes a moment. Be careful with your parentheses, it's really easy to accidentally get that 10 to the minus 20 on top. 0.905 times 10 to the minus 20. And I get a wavelength of 4.022 times 10 to the minus 6 meters. Now, this problem specifically wants it in micrometers, but then it's just 4.022. Because a micrometer is 10 to the minus 6 meters. Did that make sense?
Yeah, but since I have different numbers from yours, I'm just trying to like make sure that I'm following all the steps.
So there is a second way to do the calculation. There's a second Rydberg equation, which really kind of doesn't involve the quantum understanding. Like I mentioned when I was talking about this piece here, when Rydberg originally did this, he didn't understand the quantum mechanics. He was trying to explain the observed emission spectroscopy of hydrogen and helium and argon, like all of these, and neon lights can all be explained through their emission spectrum. And at the early 1900s, this was considered one of like the great mysteries of the physical world. And Rydberg, without really understanding the quantum mechanics, said, look, I came up with an equation that gets the right answer. I don't know why it works, but I've got an equation that can explain the different lines we see from an emission spectrum. And that equation is 1 over lambda equals Rydberg constant times 1 over n1 squared minus 1 over n2 squared. But this is for, when we're doing this one, this only works for emission. And so necessarily, I've got to get this right, N2 has to be greater than N1. Yeah. So since this only works for emission, N2 has to be greater than N1. This question happens to be for emission, so it works out. You'll notice this Rydberg constant, I didn't put the subscript h there. This is a different Rydberg constant. And this equation was really just experimentally kind of figured out. They didn't know why it was 1 over n squared. They didn't know why it was this constant r. It just worked for the explanation. Quantum mechanics came back like 5 years later and was able to explain why it was r and why it was 1 over n squared. And man, that stuff is really neat, but again, outside the scope of this class. So let's go ahead, and you'll notice this is where Dr. Campbell was talking about it being 1 over lambda. So you got your 1 over wavelength. I'll give you a quick hint. The reason it's 1 over wavelength is because the energy of the photon is equal to hc 1 over lambda. That's where the 1 over wavelength comes from. But again, Rydberg didn't necessarily understand that. So if we go ahead and we solve this, we can go ahead, we can say 1 over lambda is equal to different Rydberg constant, 1.097 times 10 to the 7. You'll notice it has units of inverse meters, 1 over meters. Which makes sense because we're looking at something in terms of 1 over wavelength. Then we're going to have our 1 over 4 squared minus 1 over 5 squared. This part's actually the same. That's going to be 0.0225 again. So actually, for emission problems, this equation is easier. I lost my calculator. Here we go. I'm going to take 1.097 times 10 to the 7 times 0.0225, again, because we already did that calculation. And we get 1 over wavelength is equal to 2.468 times 10. I'll put explicitly 10 to the positive 5. And that's going to be in units of 1 over meters. So not a wavelength. we go ahead and say, okay, now I have to flip the left-hand side of the equation. I'm going to flip the right-hand side of the equation. So lambda is going to be equal to 1 over 2.468 times 10 to the 5 meters. And if you flip that, you get a wavelength of 4.05 times 10 to the minus 6 meters. You get the same value that we just got. Right? This is mathematically and kind of conceptually, this works out to be the same thing. The difference in the Rydberg constant has to do with the definition of the energy of a photon. The 1 over wavelength also comes from the energy of a photon, hc over lambda. But this one, as long as we're dealing with emission, and as long as N2 is bigger than N1, this works great. It's a little bit simpler even. But I feel like it misses out on kind of the atomic understanding of what's going on. This does both the steps we talked about in one quick step. But it's really easy to lose track of kind of the physics that are going on there. Does that make sense too?
Yeah, the only difference is that when I actually plug that into my calculator, I get like the whole number, not the scientific notation. So I would just have to fix it and adjust it to that, because that's how it would be. I think that's how it's going to show in the answer on lab column.
Yeah, probably. You'll get something that's in scientific notation there. And then let me do this last step. I forgot to do this last step on the previous problem. But to convert to micrometers, we're going to say 1 micrometer is 1 times 10 to the minus 6 meters. Notice meters cancels out. We'll just get micrometers, and the 10 to the minus 6 is gone. And we'll just get 4.05 micrometers. So it turns out that the problem question actually kind of gave a hint of what the answer was going to be, because it asked for the answer in micrometers, and that's kind of a weird unit to ask for unless it already knew that the answer was going to be on the order of micrometers.